Thank you for choosing to watch this informative video. By choosing this video, you have opened your mind to learn about the instrumental technique called photoacoustic spectroscopy. As the name sounds, photoacoustic spectroscopy deals with two types of energies in the forms of waves, both light and sound. You might ask yourself, how exactly does this work? Absorbance spectra cannot be obtained from two different types of energies at the same time. If you ask that question, you are on the correct path to understanding how a photoacoustic spectrometer, or PAS, works. To introduce you to the instrument, a laser photoacoustic spectrometer, or LPAS, diagram is shown and will be explained piece by piece. The source of excitation for the sample is a laser which shines through a cell to a detector which reads the wavelength of light energy. The wavelength does not usually change in a pass due to the fact that the wavelength is the dependent variable, or X value, in the resulting spectrum. This will be explained more a little later. The cell through which the laser light passes is the container for quite a few components: a carrier gas, a microphone, and the sample. The carrier gas flows freely and continuously into and out of the cell and is normally chosen to help the sample provide the greatest and most resolute signal in the resulting spectra. The sample, once excited by the laser light energy, will begin to vibrate and produce what is called a resonant frequency. The resonant frequency is directly correlated to the concentration of analyte in that substance. The microphone component detects the resonant frequency and transmits the signal further down the instrument to the amplifier. The amplifier simply does one job. It amplifies the resonant frequency enough so that the signal can be converted into solid data for the spectrum. The oscilloscope receives the amplified resonant frequency and the wavelength of the laser and converts and sends the data to the computer. The computer then plots the data on a spectrum for analysis. As with all instrumental techniques, there are advantages and disadvantages to using PAS over others. An advantage of using PAS is that it has little to no interference signals. Due to the nature of the microphone being inside the cell, which is sealed off from external noise, the microphone is less likely to pick up sound interference. Conversely, an ultraviolet spectrometer could have nicks, smudges, or lint on the cell which would interfere with the absorbance of the sample and detection by the instrument. Another advantage of PAS is simple. The ability to have an amplifier amplify the signal is highly useful. Regardless of how small the resonant frequency may be, the amplifier can usually increase the sensitivity of the oscilloscope and overall instrument greatly. A disadvantage associated with using PAS is that the cell is temperature dependent. This is due to the fact that any energy can affect the excitation and subsequent vibration of the sample. Therefore, the temperature must be constant and uniform over the entire cell. Another disadvantage to using PAS is that it is cell length dependent. Sound waves or vibrations can echo over certain distances. This can cause distortion or even mimicking but separate peaks. Because the instrument is able to be tuned to each experiment, limits and ranges vary greatly depending on the sample being analyzed. Factors such as cell pressure, cell temperature, cell length, and carrier gas can each affect the instrumental process in a different way. The best way to explore the limits of detection is to finely tune each component to maximize the analyte signal, and then experiment with increasing concentrations of sample. If you would like to learn more about photoacoustic spectroscopy, I recommend reading Resonant Photoacoustic Detection of Carbon Monoxide with UV Laser at 213 nanometers, which is a research article composed by A.A.I. Khalil, M.A. Gondal, and N. Al-Suleiman. You can find the citation of their article for better searching in the comments below the video. Thank you for watching.